Okay, so we're going to do this with Manticore on our smart contracts for the CTF. So Manticore is this open source symbolic execution engine from Trail of Bits. And it can do everything that you would expect an engine to do. You can step through programs and follow any branch. You can use it to search for program states that meet a given criteria to search for. And then it comes with a solver, so it allows you to solve with for symbolic variables given the path and all the other constraints to produce concrete values for you. And then this is all written in Python, which a lot of these tools are written in Python, so you'll get some practice with that. And then here are some other ones, Oyente and Mithril, that are also used to do this kind of program analysis. Okay, so we are going to use Manticore to automatically find solutions to 4 of the CTF levels. And if you really like this stuff, your final project could be using Manticore to solve any of the other ones, if you'd like. Okay, so I am now going to just step through some of the Manticore labs to get you started. So the first thing is that this thing assumes that you have done 5.1. So 5.1 has you bring up an Ethereum Light node on Google Cloud and then connect up your wallet to it. Because all of the transactions into your CTF have to be done with your wallet address. So you have to export your wallet keys from MetaMask and then import it into the Geth Light node running on a Google Cloud Platform VM. So you're going to create a VM running Ubuntu on Compute Engine. You're going to install Docker on it. And you're going to run the course container. And the course container has all of the Manticore libraries installed in it. And it has a directory that has cloned the Go Ethereum client on the Light node client, or it's actually the full node client on it. And then what you'll do is you'll build Geth, and then you'll use it to do the symbolic execution. Okay. It also has the source code for the CTF levels in it. So what you're going to do is you need the Manticore engine to be able to compile the CTF level scripts in order to symbolically execute it. So out of convenience, we just put all of those levels in the container itself. Okay. It also contains solution templates for the 4 levels that you're going to solve. And the idea here is that we're going to give you all the framework for creating a Manticore script that solves these levels automatically. And we're just going to have you fill in a tiny amount, just a small-ish amount of the Python script for you to get it up and running. Okay, the other thing the lab does is you're going to have to run Geth in the background continuously. Otherwise, you're like when you bring Geth up, you might have to wait an hour for it to catch up. Because it actually needs, in order for any of these labs to work, you need a Light node that's up to date so that it can submit transactions into the blockchain. If it's not up to date, then the transactions are going to fail until it is up to date. So this is one of the things that hopefully you have your VM running 24/7, and then it's in a TMUX session. I have you practice using the TMUX sessions. So you'll run it interactively within TMUX, and then you'll detach the TMUX session, and then you'll be able to walk away and then come back and then have your thing running still. Okay. So there are 4 levels, 5.2 to 5.5. I'm going to first walk through the donation level, and then I'm going to interactively solve it, show you how to solve it. And then hopefully if you want to play along, if you have a computer, you can actually do this. The first thing I want to talk about is the 4-byte function signature for the ABI. So when a wallet wants to send a transaction to a smart contract, it does so by attaching something called message.data, and this has both the function it wants to call and all of the parameters to call it with. And this is part of the ABI. So all of the function calls that you can call in a smart contract are part of its ABI, and the way to access individual calls in the ABI is via this 4-byte function signature at the beginning. And so here's an example. I want to call set vulnerable contract, and I want to supply a parameter address. And so what my client will do is it will take the KEKAC 256 hash of this. And if you take the hash of it, you'll see that this is the hash. And then Ethereum defines the first 4 bytes of this hash to be basically the calling hash. The function ID is what that does. So then when the client sends something like this, so when the client wants to call set vulnerable contract, it basically sets the message.data to the first part of this data is set to the first 4 bytes of the hash of this function prototype. And then what happens is that the next thing that is attached to message.data is the rest of the parameters for the call. And in this case, it's the address, the 20-byte address, plus the padding for the parameter. And so I have highlighted that in blue. And so these are the 32 bytes of the address. So this is important. You have to keep this in mind because this is the stuff that you're going to make symbolic. Because you want Manticore to find a transaction, a winning transaction, when sent into the contract will get you all the money out of it. And so this is your input. This is your lambda that for pretty much all of the Manticore scripts, this is your lambda that you're going to make symbolic. There will be this function call that says make symbolic buffer. That's what this is being attached to. And one of the parameters for that make symbolic buffer is, well, what's the size of the buffer that you want to make symbolic? If you wanted to make this entire thing symbolic, this would be 4 plus 32, so you would be making a 36-byte symbolic buffer if you wanted to basically identify a payload of this size. Okay. So now we're going to solve the donation level, and the donation level is pretty trivial because all we need to do is withdraw. We need to just send the contract this function call, and we'll get all the money back. But this is more of a way to show you how the mechanics of running Manticore work. So this is the script I'm going to walk through. If you go into your container and you go into the Manticore scripts, in the donation in the Python donation file, you'll see this. And so the first thing that it does is that it imports the Manticore EVM. So what's happening is that Manticore is basically got an EVM built in, and that EVM is instrumented to be able to execute on symbols. So that's the first part. And then the next part of the script is to get the wallet address and the donation contract address to attack. So you need to specify your wallet address and then your donation level's contract address. And that's what this does. And so it'll take it from the system arguments. So the first parameter is your wallet address. The second parameter is specified as your contract level address. And then if you want a different file specified, you don't have to touch this. This is hard-coded to the donation file, but that's what this is, the solidity file that you're trying to symbolically execute. Okay, the other thing that happens is that you specify the gas that you want to deploy any attacking transaction with. So this is just hard-coded to be 100,000. And then the contract balance, because what you want to do is you want to tell Manticore, is there a transaction that will get back the contract balance into my wallet? So that's what's specified here. And of course, since we're solving donation gets deployed with 0.05 ETH is what donation gets deployed with. So we want to find a winning state that gets us the contract balance into our wallet. And this will be used later on in the script. Okay. The next thing the script does is it reads in the source code of the contract from the solidity file above. So then this is basically just a string that reads the solidity from that file. And then this is where the action begins. The first thing you do is you instantiate a Manticore EVM using that call. And then you create a user account. So you need to get a virtual user account in the Manticore EVM. So that's what this is. You say m.createAccount. And then the from address is taken from the parameters that you pushed in there. And then the balance of this is going to be the contract balance, because we're going to actually have to deploy this contract in order to steal the money away from it. And this is all being done within this virtual machine. It's not actually on the blockchain yet. But then we're going to get a handle on the user account. And then the next part is to create the contract. So in this case, you have contract account, and then there's a method in the Manticore EVM called solidity create contract. So the first thing we do is we're going to specify the source code of the contract we're going to create, and that was from the previous step that we read in. We're going to say the name of the contract in this source file that I want to instantiate is donation, and this is because you can have multiple contracts defined in a single file. So this just says, just instantiate the one called donation. Specify the account to launch the contract, and we're actually going to launch it with our own user account. In the CTF, the launcher creates the contract. So technically, if you wanted to be really accurate, you'd find the launcher address. But in this case, it doesn't matter. It doesn't matter which account creates the emulated contract. And then you specify an initial balance that you want to send to this contract account. And so that's what was specified earlier. So you're going to send 0.05 ETH into this contract, and then the constructor doesn't take any arguments. So that will virtually create that vulnerable contract in the Manticore EVM. Okay. And so the Ethereum contract has that entry, a single entry point that basically takes message.data and then dispatches into the function, the smart contract execution. And so it does this by looking at the first 4 bytes of data and then calling the appropriate function based on that signature. And so we saw earlier it's generated as the first 4 bytes of that hash. And so in this particular level, we want Manticore to automatically find that function, withdraw money from suckers who fell for it. We want Manticore to automatically generate the transaction that calls that particular function. And so the way we're going to do this is that we need to make message.data symbolic, because that is basically what Manticore needs to solve this level. And so because for the donation level we have this single function that doesn't take any parameters, we know that we need to make the symbolic arguments a 4-byte symbol. So this is what we're going to inject into message.data in the Manticore script. Okay, so this is what it looks like. We're going to create an attacking transaction, m.transaction, using our user account, using the victim address. And then for the data, for message.data, we have our symbol. That is the symbol that we just created, and we're saying we're making that input symbolic, and we're going to have Manticore solve for what that thing should be. Okay? And then we specify gas as a hard-coded value previously. Okay, and so now Manticore can use this transaction with that particular symbol, and then it'll automatically try and derive what that symbol should be. And so this is the main symbolic execution loop in the script, and it basically goes through that logic that I went through earlier about how symbolic execution engines work. It goes through all of the states running to see if your condition has been met. And so for all of the states in your running states, basically set the world to whatever the platform state is, and then you check for this one constraint. If this state can have this particular thing be true, it says world.getBalance of user account address is equal to the contract balance. This means that you were able to retrieve that 0.05 ETH out of that transaction via symbolic execution. Because you started without having that. After you instantiated the contract, you have 0. But then you're asking the symbolic execution engine to get that back, to get your contract balance back. And then if it is true, then I'm going to add the constraints. I want you to add in the apply the constraints that allow this to be true. And then I want the engine to give me a concrete solution to this. And that's what this is. It says state.solve1, the symbolic arguments. Concretize the symbolic arguments. And in this case, I only want one value. But because you could have multiple values that give you a successful state, you can actually say, solve for multiple here. But in this case, we only care about the one transaction that'll get us our money back, so any of them would work. So that's why it's state.solve1. And then this will derive us the concrete arguments that we can send to solve this level. And then this is what this print statement does. It formats a send transaction using the bin ASCII sort of representation of the arguments that we just derived. And then it uses our from address, and then it uses the to address of the victim, and then it exits. And this is the thing, when you get this output, you can copy and paste this into Geth, and then it will automatically solve the level. So this is what I am going to, this is what it looks like. When you run Python 3 donation solution.py, after you've filled out, I don't know, actually I think this you can run straight up. You give it your wallet address, you give it the victim address, and then after you execute this, you get that this is the transaction that you want to send from your wallet to the victim, and it turns out that this 4-byte hash is basically the first 4 bytes of the function that you want to call. And then you copy and paste this into Geth, and then you can solve the level. And if your Geth isn't up to date, you'll get this error. No suitable peers available. And so you can't submit a transaction unless you have a peer that's fully up to date on Ethereum. So that's what that is. Okay. And then you're going to show some screenshots of this. I'm going to briefly go through the next level and then show you how to solve the donation level interactively. So the next level is piggy bank. And if you recall what the piggy bank was, you had this collect funds in the base class, and then you had Charlie's collect funds in the derived class. And it's basically similar to donation, except before, when we were looking in the donation one, you saw that for this, all you needed was the 4 bytes for the function signature. For Charlie, you have both the function that you need to call as well as the parameter. And so how big is this parameter in bytes? How much is a uint 256 in bytes? It's 32. So then you would need, instead of a 4-byte symbolic buffer, you need a 36-byte symbolic buffer. And that's basically the only difference. And so that's what, in the scripts, you'll see something like this. 4 plus 3 question marks. And that's for you to fill in. Based on your knowledge, this is trying to get you to understand like what's going on underneath. You're making 36 bytes symbolic because you're trying to find not only the function to call, but the parameter to call it with in order to get the contract balance. So that's the next level. And then I want you to solve that and show the screenshots of this. So for the mechanics, I'll go over the other two on Wednesday. So I want to show you what this looks like interactively. So here is my VM that's got the container running on it. what I'm going to do is, so you've probably already solved this. What you'll need to do is get another, you need to redeploy this contract. So click on this reset challenge for 0.05 Ether to get a new version to solve. So I'll unlock my wallet and confirm this. And then while I'm doing this, I am going to attach to my running Docker container, which is here. And on this Docker container, I have a tmux session that has multiple things running. So I have my geth light node running in the background. And I have an interactive shell. So here you can see I've got at least, I have 3. So I have the 0, 1, and 2. I did a tmux attach. So if you go through 5... you see the square brackets here? That's the 0. This is the active one. And then there's 1 colon, and then 2 is 2. Did I list it?
I mean, I was just wondering how do you...
Oh, tmux. Anyone know tmux? Tmux ls. Okay, 3 windows. Can I do tmux ls minus l? No. Yeah. So I had you in 5.1, you're running this in the background, and you can see I'm up to date. And then in another window, you're, and actually let me just show you this, just to make sure I can get you there. Whoops, I didn't want to do that. So this assumes I have all of this set up, but this is in the window you see here that's doing that's synchronizing with the blockchain. That's this command, and then you want this to be running in the background all the time. The next thing I have running is an interactive session. That after I've imported my key, I've got this interactive session into geth, this command line session that gets me this. And then I've basically imported my wallet key. And after I import my wallet key, all I need to do is unlock the wallet in geth, and then I can submit transactions using this key that I've established in geth. And that's what I'm going to be using to submit the transactions. Yeah, so what I do is I exec into the container. I start the container. I do a shell into the container. And then within the container, I've installed tmux. And then I execute tmux. And then I start geth. And then I create another tmux session to do an interactive geth. And then I start another tmux session to get into the Manticore scripts. Because they're all running on that container, and you do need multiple windows on that container to execute the lab, yeah. Yeah, I installed it for you. So yeah. Yeah, I'm trying to streamline a little bit, but yeah, there is tmux in that container that you instantiate. In fact, I think there might be tmux in the VM itself. You could, the other way to do this is to tmux the VM and then do multiple Docker execs into the container. But this is, for me, this is my workflow. But like you're free to if you're good at tmux, you're free to do other things, yes. Mm-hmm. Yeah. I call them sessions, tmux sessions, but they're all running in this one window. And I just do Control-B P and Control-B N to go back and forth between I have 3. So I'm going to show you the 3-session way of solving donation as an example. So this thing is every 15 seconds or so is a new block on Ropsten. And so hopefully you'll see this increment 209 periodically. I hope that's still up, because otherwise my stuff won't work. Okay. So the next thing you would need to do is unlock your wallet. So you've already imported your wallet in the interactive get node. I'm going to unlock it. And when you import your account, you import it with a password. And so it'll ask you for this. I think you have to do this every 10 minutes or so. Otherwise, it's left open and is insecure. So this is me unlocking my account. And then this is also in the container. You see I have all the different scripts for solving these levels. This is a donation solution that I have. And you can see this is basically the program that I just walked through. So I can execute this with the addresses, my own addresses, and then figure out how to solve this. So what I'm going to do is I'm going to say Python 3, donation solution. I'm going to copy my address from MetaMask. And then I'm going to go into the C. So by now I've probably instantiated this. So now I can play this game. So this is the new level I've just instantiated. I'm going to copy the address. And then I'm going to ask Manticore to solve for the transaction that will solve me this level. And you ignore the error. And then it's given me this level. And you can see for this, it's found the thing that I want to call. So then what I would do is I would just copy this, go to the previous interactive get session, and then just paste it. And then it'll give me this transaction hash. And so I've sent this transaction on my behalf to the victim contract with this as the data, and that's going to call the function, and then wait for it. And then you win it. Okay. So the other ones are just like this. They're just slightly more complicated. What we're going to do this week, so I'm going to stop now. I'm going to ask you to just start trying to solve these things. And then we're going to take this week to basically try and solve as many of these Manticore levels as we can. The next 3 are probably easy. It's the last one that's the really gnarly one. So yeah, I'm going to spend the whole week on this thing in order to get it done before the last week. So are there any questions about what I'm having you do? Okay, just let you get started then.
You mentioned the last one's hard. Is that because it has those traps that are baked into it to make this difficult, or is it just like...
It's because of Manticore is not set up in a way that's very nice for us to deploy a contract and then have... So we're deploying... This is a reentrant... The trust fund level requires you to deploy an attacking contract, and then there are some symbols in the attacking contract. These things are just instantiating a transaction. So you'll see with trust fund, you're actually instantiating an attack contract and using the attack contract to exploit the victim, and then generating all of the transactions to not only deploy the victim, but to actually get the money out of it. So it's a gnarly level. It's a stretch goal for sure. But yeah, that's why it's hard. Okay. So last class, we walked through how you would solve the donation level, and I showed you all the steps in a demo. And then the next one was this piggy bank one, which is it's very similar, except the only thing that's different is that the size of your symbolic buffer has to accommodate the parameter that you're going to use for that call to withdraw the money from the piggy bank. So those two were your sort of your introduction to symbolic execution, and those were meant to be hopefully solvable without too much of an issue. If you're spending hours trying to solve this thing, come to my office hours because it should not be that difficult. Yes? Yeah, so if you look at this vulnerable call, you want Manticore to figure out a way to call this call to get all your money back. So that's the constraint in the Manticore script. But in order to do so, Manticore asks you to, you're making message.data symbolic, and you're saying, give me a message.data, which is the way we do the function call in Ethereum. Give me a message.data size that you want to make symbolic. And what is part of message.data, the first 4 bytes, is the hash of the function you want to call, and then the rest of the bytes are the parameter list. How many bytes of the parameter should I make symbolic? Oh, I'll get through I'm walking through the lockbox. But this one, yeah. So you have the function hash, which is 4 bytes. And then you have the parameter that you want Manticore to solve for. And that's, this one's a 32-byte quantity. And that's why, in fact, the answer is 36. So when you look at this, and the intent is to get you to think about what exactly is the symbol I want to inject into the script that I want Manticore to solve for. And the symbol in this case is, what is that message.data? What is that? So you're going to say that these are the arguments that I want to make symbolic, and message.data is 36 bytes. That's the symbolic call. If I had another uint 256 as another parameter there, then I would have to add, it would be 64 plus 4, it would be a 68-byte symbolic buffer. You could actually make this like hundreds of bytes, and it would still find the correct solution. It would just take longer, because then it's searching through a much larger input space for the symbol injection. Okay. Yeah, so yeah, it's not quite that's exactly right. We're sort of cheating. We're like, oh, the function that we want to call, we want Manticore to try and find this, and we know exactly the number of bytes. But that's right, that's kind of cheating. That's not really automatic. If we really wanted to do this right, then we would set message data, the length of message.data, to the maximal length of the parameter list of a function in the victim contract. And that's something you could automatically scan. And in the ABI, you can just statically scan it, find the maximum length, and then make that the symbol. Make that the length of your, you would scan the ABI, you figure out the function call that has the largest list of parameters, and then the size of that is what you would make symbolic. Yes?
So if you're calling a contract in this way with a buffer that's too large, does it just ignore the extra stuff?
Yes, it will, so yeah, if it's way too large for the actual exploit to work, yeah, it will give you a solution that might have that stuff pruned. In fact, it will, but it will take longer to find that. And I don't want you to sit here for like weeks finding a solution. So that's the other thing. These scripts are meant to get a solution within like 5 minutes, especially the last one. It's going to take a little while to run that one. But yeah, these things aren't going to be like, I'm trying to make it so that the script, when you run it, you get the carrot almost immediately. But in reality, what you're saying is right. Like, we've actually stacked the deck in our favor with these scripts to make it run fast, but you wouldn't necessarily have that in real life with a larger contract. Yeah. So yeah, these are, as you have already discovered, these are basically toy examples to just show you the technique of this. Okay. So the next two levels are a little bit harder. The first is lockbox. And just to jog your memory, because this might have been 3 weeks ago that you probably solved this level. So this contract unlocks when you give it the correct pin. And the pin is calculated using the value of the timestamp that was supplied in the block that the contract was created in. Okay? And that's here in the constructor. It sets this pin to be the block timestamp of the current block, mod 10,000. It's a 4-digit pin. And then all you need to do to unlock this lockbox is to call the unlock function with the correct pin. And then it will transfer the entire balance of the contract over to you. Okay? So let's walk through the Manticore script. Manticore, the setup is very similar to piggy bank. In fact, rather than the withdraw with an amount, you have an unlock call with a pin. So the symbolic buffer is going to be the exact same size, right? You have a 256-bit parameter, you have a 4-byte function, so the make symbolic buffer will also need 36 bytes as an exact call. But there is an issue here. The Manticore virtual machine has to know the value of that timestamp in real life, right? It can't magically generate the exact timestamp that your CTF level was deployed on. So you actually have to supply it to Manticore, and then Manticore will automatically figure out that, yes, the last 4 digits of the timestamp are being used to unlock that contract. So that's the additional piece that you have to add to Manticore's EVM in order for Manticore to be able to automatically attack this level. Okay, so the same thing happens where you're setting up the EVM, but in Manticore, the EVM can be configured with custom world state. So you can specify different parts of the Ethereum virtual machine that have specific values. And specifically, you're going to figure out what this timestamp was in your real life contract, and then you're going to specify it in the Manticore EVM to create this contract with. So that's what we're going to do. And this is done in the Manticore scripts directory. It's done with this Manticore EVM custom state class. So that's how we do this in Manticore. And this is how you do it. You first instantiate a blank constraint set, and that's something within the Manticore package. So these are constraints on the EVM that you're going to actually initialize to be what you need them to be. We're going to start by initializing a world state that uses these initial constraints and then updates it with the timestamp that you want to create this EVM with. So what is the timestamp of the EVM when I start up the Manticore machine is what you're specifying here. And this is the timestamp of what this is from. You want to set this timestamp to be the timestamp of your lockbox contract when it was created. So this is the step where you're going into the Etherscan, finding the timestamp, converting it into seconds from the epoch. So this will be a large number that specifies seconds from 1970. And that's what you're going to fill into the Manticore script. And this will start the Manticore EVM on this exact timestamp. And then what you can do is you can create the lockbox contract from here, and then it'll have all of the state initialized just as it's been initialized in the real blockchain, in the Ropsten blockchain. Okay, and then what you do is, so this is all done for you. I'm just explaining what's in the script for you to understand what's going on. You create this initial state with those constraints in the world, and then you instantiate that this custom state object. And then from here, you can then solve for the input. And you perform symbolic execution as you would before. So this actually creates the EVM with your custom state. And then with this EVM, this M, we're now going to go through and run the symbolic execution engine on the lockbox contract. Okay, so that is basically the script. Are there any questions about, does that answer your question, Wen? Okay. So it's a relatively, I think the question marks, that's the main thing that you're basically being asked to solve. And then in the script, it includes the lockbox source code so that when it does the deployment with the exact source that you're attacking. Okay, and then show the screenshots of the execution of the script as well as the transactions being submitted to Geth. And then that last transaction where you're transferring the ETH from the level contract to your own wallet. Okay. So this leads us to the last Manticore level, and this is the hardest one. This is the hairiest one, the trust fund one. So if you remember the reentrancy attack, this is the thing where you're doing a recursive call back into this contract. So the attacker calls a vulnerable function, split DAO, and then this split DAO will eventually reward the sender with some money. And then by paying out this amount, the attacker in the fallback function of the attacker will then recursively call that call again. So we want Manticore to automatically do this, which is no small feat. So this is the trust fund level, and we're going to ask Manticore to generate the transactions that will allow us to exploit the trust fund level automatically. And so this is the attack on withdraw. And fortunately, withdraw is just a 4-byte reentry string. So when we're doing the reentrancy attack, all we're doing is calling back into this withdraw function with no parameters. So our symbolic reentry string is only going to be 4 bytes. So if you look at this withdraw contract, it has you do this transfer to the fallback function before it updates this withdrew this year state. And so if this fallback function calls back into withdraw again, then you can do this withdraw basically 10 times and suck the balance of the contract out before this withdrew this year state is set to true, and then you can wipe out the contract balance. So if you have not done this level yet in the actual CTF, do that one first. Otherwise, none of this other stuff is going to make much sense to you. So yeah, get the trust fund level solved first, and then do this the automated one next. Okay, so your trust fund attack contract should have something that looks like this. And so this is an example of a solution for the trust fund level, where in this call, I have this proxy call to make the initial call into the vulnerable contract. So something has to kick off the first transaction, and that's what this thing does. When I call proxy call, it instantiates the trust fund level, and then it just calls the initial withdraw function with that on that address. And then in the fallback function, to create that loop, I am going to create while count is greater than 0, and I set the count to 10. What I do is I decrement count, I instantiate the trust fund contract again, and I call into withdraw an additional time. So there are two things, the two main things in this reentrancy attack script. One is to do the proxy call first, and then to do the fallback, to implement the fallback to get that thing to recurse. Okay? So we want to use Manticore to solve this level automatically, or as automatically as we can. There are two options for doing so. There's the really hard option, which is what the Code Lab is going to walk you through, to do this exactly. And then so in order to do this exactly, we need Manticore to calculate the exact transactions and the exact addresses to use in those transactions that you can just cut and paste into Geth. Now, in order to do that, you have to give Manticore all of the addresses and all of the nonces associated with all of those addresses for it to automatically generate the transactions. And so if you have done the rainy day fund and you have understood how hard it is to get all those nonces, that's what this exact option is asking you to do. So you can do this. We have gone through and done this exactly. Or the other thing you can do is the inexact option, is to have Manticore just find the payloads and then manually fill in the contract addresses because it's going to generate incorrect addresses unless given the correct nonces. So this is the second option if you can't get the exact option to work. I am going to walk through the exact option. Yes?
How many nonces do we need to find to get the exact option?
2 nonces. And you have to get both exactly correct, otherwise the thing won't work. The 2 nonces are the nonce of the launcher for trust fund, and this is the exact same way you did the nonce for the launcher for rainy day fund. You would do the exact same thing for trust fund, and then your own wallet nonce. Those are the 2 things that you need in order to get the exact method to work. And both have to be correct, otherwise you'll get transactions that will fail. And if you do have transactions that fail, it's because the nonces are incorrect. Now, one of the things about the exact way is that if you have guessed incorrectly on one of the nonces, the script will detect that and error out. Because we have you supply the address of the level contract, and it makes sure that the nonce that you give for the launcher actually corresponds to that address. So there is an error checking piece of the Manticore script. So we're trying to make it easy, but Manticore doesn't make it as easy as you would like to do this, which is why we added this check on top of it. Okay. All right. So in order for Manticore to solve this level, Manticore is trying to be like you, right? You need Manticore to generate an attack contract so that it can instantiate that contract and then issue the reentrancy call. And so to do that, Manticore supplies this generic reentrancy exploit script. And so this is, if you look at the Manticore script to solve this level, you will see a variable called exploit source code that is a string, and that string is basically this, the text for this generic reentrancy exploit contract that you're going to deploy. And so what Manticore is going to do is it's going to deploy this contract and then use this to solve the level for you. Okay, so that's the first step. And you can see it here. Part of the things that are parameters to this generic script is the number of times you want to do the reentry. So that fallback function has that loop counter. That's basically what one of the parameters is for this generic script. The other one is the address of the vulnerable contract. You want to be able to point the attack contract to the victim contract. And so this will be something that you'll set with a transaction. And then the address of yourself, the owner. So you want to be able to get the money back into your own wallet. So that's another thing that you can set, that this generic reentrance script will set. And then finally, the next big thing is the reentry attack string. How am I gonna, what do I need to send to the vulnerable contract in order to perform the exploit? Right? And in this case, it's the 4 bytes that call into the withdraw function of the victim contract is what this is going to be. Okay? And you can see when you initialize this contract, this is basically the constructor. This is the old way we used to do the constructor in Solidity. It sets the owner to whoever launches this, and this will be your wallet contract that you send into the Manticore script. Okay, so then the idea is that the Manticore script is and I haven't shown the entire exploit here. I'll go through the rest of the exploit in a second, but the idea is that Manticore is going to deploy this contract and then generate transactions to this contract that will cause the victim contract to lose all of its money. Okay? Okay, so the generic contract has some additional calls. One is to set the vulnerable contract address. So it supports a setter that specifies this address. So we saw before this address, we don't know this address, it has to be given it. So that's a setter for the vulnerable contract address. We have the setter for the reentry attack string. What are the bytes that I'm going to send to the victim over and over again to do the reentrance? And that's what this does. So another setter. Another setter for the number of reentrances that I'm going to do. And then the initial proxy call. So just like I had a proxy call before, I'm going to have a proxy call that will kick off the exploit. And in this case, you can see that address call with this value, this message.value with the data. And this will directly call a function inside of the victim, and hopefully that function will be your withdraw function. It should automatically find that you need to call withdraw and then send it through here. Okay, so what Manticore is going to do is it's going to deploy this contract, and then it's going to generate the transactions to set all of this stuff up, and then the final transaction to kick off the exploit. And then by doing so, it'll automatically generate the result. Okay. So the next part of the generic script is the fallback function. And so this is similar to the proxy call, except it's in the fallback. I basically have the reentry repetitions counter that I look at. And as long as this is greater than 0, I just call back into that exact same thing, that exact same call. Okay? And then finally, I need to get the money back. And so there's a call called getMoney that allows me to get the balance back. Because in the end, so I'm telling Manticore I need a state, an EVM state, where I get all the money out of the contract. And so the final transaction that Manticore will spit out will be this one that actually gets the money out. Okay. So I'm going to go through the details of the Manticore script now. The first part of the script defines a utility function called setNonce. And setNonce, given a particular world and a particular wallet address, and a nonce that you want to associate with that address, it sets that address as nonce to whatever you specify. And this looks really crazy that you're going to increment this one at a time. This is because this is what Manticore supports right now. So you don't see that very often, where I'm like, in order to get a nonce of 256, I'm going to call increase nonce 256 times. That is what is actually happening. Maybe they fixed this already, but use that as, it doesn't matter. We're just going to use it as a black box. Okay, this is the next part of the script, and you see the 3 question marks is what is the contract balance that you want to get back. So this will help you with your final state that you want Manticore to achieve. And I think this is like 1 ether. I don't remember. Trust fund is 1 ETH, perhaps, and that's given in the amount. Those units are in Wei. The next part of the script creates these accounts on the EVM. So the creator account is, the address of the creator account is the level launcher. So just like you figured out the level launcher for rainy day fund, you're going to figure it out for trust fund, and then you're going to create that. So this gets specified as part of the parameter list that we'll see later. So you just have to supply that yourself. And then you create that account with a particular balance. Because we're going to deploy from this creator account, we're going to actually deploy the level from here. You have to specify that you're going to deploy it with the full contract balance of the account. And then the attacker account, which is your wallet address. So you specify your address here, and then the balance of your attacking balance. So this is going to be 0 because initially you don't have any money in your wallet initially. Okay, the next part of the script, this is the tricky part. You have to set the nonce for the CTF level launcher. And in this case, It's specified here as the last parameter of this. So this is the address, and this is being done in the EVM, right? The EVM is trying to recreate the same state that's outside on the real Ropsten network, and this is the key state that the EVM needs to solve this level. And so the mechanism for doing this, you go to the transaction that created the level contract, you go into state changes to view that, the state changes of the wallets associated with this transaction, and then you can find the launcher and the nonce of the launcher. The alternative, the inexact way, is to just set the nonce to 1, ignore the warnings, and then you're going to have to patch the addresses up after the fact. And then the next step is to set your wallet's nonce so that because it's your wallet that's going to deploy the generic attack contract. You can also set this to 1, but this is actually quite easy to get. And then by setting that, it will understand it will know what address to send the exploit transactions to. Yeah.
So the nonce for the level launcher is you need the nonce that created your victim contract.
Yes.
But for your own wallet nonce, you need your current nonce because you're going to create a new contract.
Yes.
Okay.
That is okay. So let me repeat that. For the level launcher nonce, you need the nonce that created that contract. For the wallet nonce, you need the one that you're going to use to create the next contract. And that's the biggest part of this level. Getting those two nonces correct will allow you to do the exact thing. And so this is the one, so this one was the prior nonce. This is the one that you're going to do next. So that's the key part of this. Getting these two numbers correct is what stands in between you solving it and not solving the level. And this is what I can help you with. If you come here next week, I can help you get these things right. Okay. Okay, so then we're gonna run through the actual transactions. We're gonna create the contract account. So this is the victim. So we have to set up the victim contract in the EVM, and this is what we're doing. We've got the contract source code that's in the file system in your container already. The name of the contract we want to instantiate. The owner, which is the creator account. So this is the level launcher account. And then the address that it got created at. And we're supplying this so that we can do a sanity check. Because based on the nonce that you specified here, based on this nonce, it will automatically check that the actual CTF level address makes sense given the nonce that you instantiated. This thing will error out if you have specified the wrong contract creator nonce. So that actually is a good thing in this case. All right. And then we want to send our entire balance for our address because we gave this address all of our contract balance. So now we're going to deploy this contract and then give the contract balance. So this is setting up the initial victim contract that we're trying to get the money out of. And then we instantiate the attacker contract. And so this exploit contract uses our account to create a contract with the generic source code for the reentrancy script here. And that's what I walked through initially. And then the owner is myself. So this is my own wallet contract, or wallet address. And then I'm going to perform the attack symbolically. So I have to ask Manticore to symbolically execute all of this in order to get me the money out of the victim contract. And this is where the magic happens. In order to do so, in order to invoke the methods in the generic script, you need to execute these calls. So the first thing is to set the vulnerable contract address. So you need to set the victim. So when you deploy the generic contract, the victim is not specified. So what Manticore needs to do is set the vulnerable contract. And then the next thing it does is set the number of reentries that you want. So this is something that you fill in, and this is easy to set because it's 10 times basically is how many times you have to call it. And then you have to create a symbolic string that is going to be used to do the actual reentrancy attack. And so you'll see this reentry string, which is a make symbolic buffer, and you'll know that that's actually a small number of bytes that you're actually solving for. And then given that symbol, you inject that symbol into the EVM using this. So then I can say set the reentry attack string in the attacking contract to be this symbol. So that is your symbol injection into that contract. And then the last thing that Manticore will need to do is call this proxy call in order to kick off the whole exploit. Now, if you look at this, this is a generic pattern, and the only thing that you don't know is what this value should be, this reentry string should be, and that's what you're sending into Manticore to say, what should that be, and automatically generate. As soon as you figure out what this thing is to get me all the money, I want you to concretize that input and then spit it out, and then give me the transactions that will fall out. And what it'll do is it'll spit out the transactions for every one of these steps with concrete values as the parameters. And then that's where the output is derived from. Okay, so that's a lot of hard stuff. Are there questions about this and what it's doing?
How do we find out what the size of the buffer is?
So this one is very similar to the other ones. If you recall the you're trying to solve for the actual message.data that will invoke withdraw. So all of these function calls in
So it's just the first 4 bytes.
basically the 4 bytes, yes. Yeah. So yeah, I'm not trying to, but these
You said the function.
yeah, I mean, but I want to tie it back into how the thing is done. Yeah. So where are you injecting that symbol? It's really good to understand that part of it. You're setting up the entire EVM state, and you're saying the thing I don't really know is the actual reentrancy string. Let me have Manticore solve that for me. And that's the whole part of this exercise. Okay. So this is where we actually call into the engine. And so we are looking for a state, and this is exactly what we had before, where our balance is equal to the contract balance plus the attacker balance, right? So if our attacker balance starts out as 0, we just want our balance to be the entire contract balance. So that's the final state. And then we add, like if we have found a state where this is true, then I'm going to add the constraint that to make it true. And then what I'm going to do is I'm going to, for every transaction, I am going to have this thing generate all of the calls needed to make this happen. So for every transaction that Manticore needs in order to solve this state, I'm going to concretize those transactions by doing a solve one. And every transaction needs the message.data, it needs the caller, it needs the from, it needs the to, it needs the amount of ether to send, and the amount of gas to send. And then if that all is concretized, it will then spit out the transaction for you in the console. And the sequence of transactions that this thing spits out, you can then just copy and paste into Geth, and then it'll just solve the level, just like in the donation level. Okay, and so after you have configured all the question marks, you run the script. And the thing that's different in the trust fund script from the other scripts is that in the trust fund script, I am specifying an extra contract creator address. So this is the level launcher address that I've used throughout, whereas before all I needed were these two addresses. Now there's another parameter, and then this you can leave alone because the actual source code is there for you in the container. Okay, so when you run the script, you'll get a bunch of transactions, and you can actually go and look at these transactions and see them mapping to the different calls in that previous slide. So here is the attack contract creation transaction. And so what you're doing is you're instantiating the bytecode of the generic script. So if you look at all of this stuff, that payload is the EVM bytecode of the generic reentry contract. And then the result of this will return a contract address that has this address. This is why we needed the nonce for our own wallet, so that Manticore can automatically predict this and use it in subsequent transactions. Because we're going to initiate the generic one, and then we're going to have to send a bunch of transactions to the generic contract address. In order for us to know what that address is, the concrete value of it, this is why we needed our wallet nonce for this particular attack. The next transaction in the list, and you can see this from the hash, is to set the vulnerable contract address. And again, this is from my wallet going to the generic contract address, and I'm going to set it to be my level contract. So if you, in this case, for my CTF level, this is the address of my CTF level contract, and this sets the victim address. The number of reentrancy reps, that is the 4-byte function hash. And then you can see I'm setting this to hex OA, which is 10. So it generated that, yes, I need 10 reentrancies. And then this is the attack string. And if you look at the attack string, actually this is an attack string that has probably 4 extra bytes in it. This is the money attack string. And if you do the kekak hash of withdraw, you'll get this as the first 4 bytes. So actually, I think on this one, I have an 8-byte message.data payload, but it still works. And then the next one is a proxy call. So I call into the generic script on proxy call, and then I use this as the calling. This is the withdraw function that I'm going to call. And then the last thing, after this thing executes, I should have all of the money in the generic script. And then I call from the generic script with the get money call, which is what this is, and this gets me all my money back. Yes?
How is the gas price set when you send these?
It's hard-coded. Because I found that, so I haven't figured out what's going on. When Manticore returns this, it returns this as a string of hex FFFFFF, which is way too much gas than you need. So Manticore doesn't correctly guess the amount of gas. So and you can see this in the script. I was hoping people weren't paying attention. But because you're paying attention, yes, I admit, I had to hard code that thing because I couldn't figure out how to get it to work otherwise. But that's what's going on. The last step, which you make sure you do this, is that you need to enable the generic contract as an authorized sender for a trust fund. So make sure you do this before you start copying and pasting those transactions into Geth. Otherwise it won't work. The last call will fail. The proxy call will fail unless you do this. Okay, so copy and paste those transactions and then show the same kinds of screenshots as before. Okay. Questions? So I think what I'm going to do, I'm going to stop right here and let you start working on Manticore rather than cover any new content. And then I'll just make Monday the advanced topics lecture. All right. Okay, so someone has already run into this. I want to make sure that this is clear. When Manticore generates these transactions, the first step has to be done in order. You have to deploy the attacking contract first. So copy and paste that to create the attacking contract, and make sure that it comes up before you authorize in the second step. Because what you have done in Manticore is say, I am specifying the nonce that the attack contract is going to be launched with. If you do this first, and then you create the contract, then it's off by 1. So just to make sure, because if you're off by 1, then this thing will immediately fail. Like these calls will fail. Okay. I want to get that on record so that, that can cause an issue.